Dear students, so today I am going to speak on the topic distortions in octahedral geometries. Here, I shall discuss about the possible deformations that can take place in an octahedral complex, giving rise to the complexes with different geometries. And a closely related effect known as Jahn-Taylor distortion will also be discussed here. First of all, we need to know what an octahedral complex is or what is an octahedral geometry. In a typical octahedral geometry or in a typical octahedral complex, there are 6 ligands that are connected to a metal center. And in a regular octahedron, it is expected that all these 6 ligands should be of similar kind. And each of the metal ligand bond lengths should be equal. At the same time, the LML bond angles, each of these LML bond angles should be equal to 90 degrees. On the other hand, in a distorted octahedral geometry or in a distorted octahedral complex, it is expected that all the ligands present may not be of similar kind. So this distortion in an octahedral complex can take place in 2 different ways. In one of the type, the axial ligands are little bit compressed. These 2 ligands are said to be present in an axial direction, and these 4 ligands are said to be present in an equatorial plane. These are equatorial ligands and these are axial ligands. And in a compressed geometry, these axial ligands are compressed. Means the bond lengths, the metal ligand bond lengths, the metal ligand lengths present in the axial direction are a little bit shorter as compared to those present in the equatorial plane. On the other hand, in the elongated geometry, the ligands which are present in the axial direction have little bit longer lengths as compared to those present in the equatorial plane. So in this way, we got distortions, 2 different distortions in a octahedral geometry. Now, the distortion in an octahedral complex is mainly due to an effect known as Jahn-Taylor effect. And by definition, if the ground electronic configuration of a nonlinear complex is orbitally degenerate, the complex will distort so as to remove the degeneracy and achieve a lower energy. That means for a nonlinear complex, we can take the example of an octahedral complex. The complex will undergo distortion or it will distort itself to remove the degeneracy or to destroy the degeneracy which was initially present within the complex to lower the energy of the complex. This is what according to Jahn-Taylor effect or Jahn-Taylor theorem. Now, here it should be noted that all the complexes are not going to, or all the complexes, all the octahedral complexes will not undergo Jahn-Taylor distortion. Now a question arises, then what are the complexes that are going through Jahn-Taylor distortion? For that, we need to know about the electronic configuration of the complexes under consideration. And if both the EZ and T2Z sets of orbitals involving a metal complex are symmetric, then we are not going to observe any kind of Jahn-Taylor distortion in that complex. T2Z means it is a set of orbital comprising of dxy, dyz, and dzx that I have already mentioned in my earlier classes. And easy set of orbital means it is a combination of two orbitals. It is a set of two orbitals, that is dx square minus y square and the dz square orbital. Now, if these set of orbitals, these two sets of orbitals are symmetric, then electronically symmetric, then we cannot expect any kind of uh, distortion in the complex. For example, in a octahedral complex of Ni2 plus ion, Ni2 plus, which is a D8 configuration. So in that complex, we have 8 electrons in the d orbital, 1, 2, 3, 4, 5, 6, 7, 8. Now we can see that the T2Z set of orbital is fully filled. So it is symmetric. And also we can see that the EZ orbital is half filled. As we know that half fill and full fill orbitals are more symmetric as compared to that of the partially filled orbitals. So EZ is a half fill orbital, so it is a symmetric one. On the other hand, T2Z is fully filled, so also it is a symmetric one. So in case of this particular complex, both the EZ and the T2Z sets are symmetric. As a whole, there will not be any kind of distortion that is going to take place in this particular complex. Now let us take an example of a copper 2 complex. As we know that in copper 2, we have 9 electrons in the d orbital. And these are the two possibilities in which the electrons can fill the 5d orbitals. So here we can see that the T2Z level is fully filled, so it is symmetric. On the other hand, EZ level, out of 4 vacant sites, only 3 are filled up by electrons. So it is a disymmetric configuration. It is not symmetric. So although its T2Z level or T2Z set of orbital is fully filled, means it is symmetric, but EZ level is not fully filled, neither it is fully filled nor it is half filled. So it is a disymmetric configuration. So as a whole, copper 2 plus complex will show Jahn-Taylor distortion. So this is how the orbitals, degenerate orbitals, will further split it up due to the Jahn-Taylor distortion, as it is observed in case of copper 2 complexes. Initially, these T2Z orbitals were degenerate. Also, they were symmetric. All the 3 T2Z orbitals were filled up with electrons, fully filled. But due to Jahn-Taylor distortion, they further split it up in two sets of orbitals, one containing two orbitals dxz and tyz, and the other one is dxy. Now these 6 electrons has to be distributed in these 3 orbitals, and this will be like this. On the other hand, the easy orbital, the easy set of orbital will be again split up into two sets of set of orbitals. One is having the dz square orbital, the other one is having the dx square minus y square orbital. Since dx square minus y square orbital is higher in energy, raised in energy, so preferentially the lower lying orbital will be filled first. So it will be the dz square orbital will be filled first, so it will be fully filled. On the other hand, the dx square minus y square will be half filled, and that makes the dissymmetry in the electronic configuration. And as a result, the result of this Jahn-Taylor distribution, the two axial ligands are elongated from the metal center, and as a result, this is the situation. This is the distorted octahedral geometry, which is observed in case of copper due to Jahn-Taylor distortion. This is the same thing actually. This is how the dx square minus y square dz square orbital. This is in terms of energy elongated, which is observed in case of copper 2 complexes, Jahn-Taylor distortion due to Jahn-Taylor distortion. So this is a D1 configuration. Here also we can see that since only one electron is there in the T2G set, means it is asymmetric or dissymmetry, for which it will also show Jahn-Taylor distortion. And due to this kind of distortion, this kind of electronic configuration, the axial ligands will be compressed, and this will be the overall geometry of the molecule due to Jahn-Taylor distortion in a D1 system. Now, this is D1 versus D9. D9 is for copper 2 plus and D1 is for the titanium 3 plus, for example. So D1 lead to compressed geometry, axial compression, and D9 lead to a geometry which will be elongated geometry. And both of them are due to Jahn-Taylor distortion. So this is how we can summarize. We can say, we can determine whether a given electronic configuration will undergo Jahn-Taylor distortion or not by looking at this picture. See, for a D1 system, you can see that only one electron is there, so it is unsymmetric. So Jahn-Taylor distortion will be there. Here also D2 system will also have only two electrons. Out of this three, only two are occupied, so it is a asymmetric one. So here also it will undergo Jahn-Taylor distortion. But in a D3 configuration, all the T2G set of orbitals are filled up. All the T2G set of, though they are half filled, but still they are symmetric, and that's why it will not undergo any kind of Jahn-Taylor distortion. In D4 system, in a low spin complex, it will preferably paired up rather than going to the higher lying easy level. So this will also lead to a dissymmetric or asymmetric T2Z level that will lead to a Jahn-Taylor distortion. So this the D5 in low spin complexes, it is also asymmetric, so distortion will be there. Now this is D6 in a low spin complex. All the 6 ligands will be paired up in the T2Z level. So it is a symmetric set of orbital. So no distortion. D7 Though the T2Z level is symmetric, but the EZ level is unsymmetric. So as a whole, it will undergo distortion. Here you can see that T2Z level is symmetric with fully filled electrons. EZ level is also symmetric. It is, though it is not fully filled, but it is half filled. So it is symmetric. EZ symmetric, T2Z symmetric. As a whole, the molecule do not undergo any kind of distortion. D9, as in the case of copper, will undergo elongation. Distortion will be there because EZ is unsymmetric. D10, it is obviously it will be symmetric and will not observe any kind of distortion in this complex. So in high spin complexes, for 1, 2, 3, it will be similar to that of the low spin complexes. This will be unsymmetric, so distortion will go on. Here, no distortion as it is symmetric. D4, D4, T2Z is symmetric, EZ unsymmetric. So distortion will be there. D5, D5 in high spin complex, it will be symmetric. Both T2Z and EZ level will be symmetric, so no distortion. But if you look at the low spin complex of D5 configuration, then you can see that T2Z level is unsymmetric, so distortion should be there. But here, all are half fill. 5D orbitals are half fill, means they are symmetric, so no distortion. In D6 system, EZ is symmetric, T2Z is unsymmetric. Overall, distortion will be there. Same case, T2Z is unsymmetric, EZ is symmetric. Distortion will be there. In D8, T2Z will be fully filled, EZ will be half filled. Both are symmetric, so distortion will not be there. D9, as in the case of low spin complexes, D9, here also we will see some distortion. In D10, there will be no distortion, as both the T2Z and EZ levels are fully filled or they are symmetric. So students, I hope that you have learned something about Jahn distortion, and the distortion that are possible in an octahedral geometry. Thank you.